Mastering graph algorithms. Advanced techniques for cycle detection. Cycle detection in graph algorithms lies at the heart of solving complex computational problems across domains ranging from computer networking to artificial intelligence. By identifying loops within graph structures, developers can prevent infinite recursion, optimize routing protocols, and enhance database integrity verification. This deep dive explores both theoretical foundations and practical implementations. The ability to detect cycles transforms abstract mathematical models into tangible problem-solving tools. Whether analyzing social networks or validating compiler syntax trees, cycle detection enables us to uncover hidden patterns that shape modern technology infrastructure. Fundamental concepts in graph theory. A graph consists of nodes interconnected by edges, forming either directed or undirected connections. In directed graphs, edges have a specific orientation from source to destination node. Undirected graphs treat connections symmetrically, allowing bidirectional navigation between nodes. Cycles emerge when following edges leads back to the starting node after traversing at least one other vertex. Detecting such closed paths becomes crucial in scenarios involving topological sorting, circuit design validation, and deadlock avoidance mechanisms. Directed acyclic graphs, DAGs. These special graphs lack cycles entirely and form the basis for many scheduling algorithms. Eulerian circuits. Special cycles that traverse every edge exactly once exist only in certain graph configurations. Bipartite graphs, a class of graphs that inherently cannot contain odd-length cycles. Detection strategies. Depth-first search approach. The depth-first search, DFS, technique provides an efficient way to identify cycles by tracking visited nodes during traversal. When encountering a previously visited node that is not the immediate parent, we confirm the presence of a cycle in the graph. This approach maintains three states for each node: unvisited, visiting, and visited. During traversal, if we encounter a node marked as visiting, it indicates the discovery of a cycle. This method works particularly well for sparse graphs with few edges relative to vertices. The time complexity remains O, V plus E, where V represents vertices and E represents edges. Space requirements depend primarily on the recursion stack depth, making it suitable for moderately sized graphs. Optimizing DFS traversal implementations often utilize recursive functions with explicit visitation markers. Some optimizations track parents separately to avoid false positives caused by backtracking steps inherent in tree traversals. Variants of DFS handle different graph types effectively. For example, directed graphs require additional care to distinguish between forward edges and cross edges during cycle detection. Union-find data structure methodology. The union-find, disjoint set, approach offers an alternative strategy leveraging path compression and union by rank optimizations. It excels at detecting cycles in static graphs where edges remain constant during processing. Each node starts as its own parent. As we process edges, we check if connecting two nodes would create a loop. If both already share the same root ancestor, adding this edge forms a cycle in the graph structure. This method achieves near-linear time complexity due to the efficiency of path compression operations. Its simplicity makes it ideal for parallel computing environments where multiple threads can operate independently. Breadth-first search variations. Breadth-first search, BFS, adaptations provide yet another perspective on cycle detection. By maintaining a queue of nodes to explore, we can systematically examine levels of connectivity before reaching deeper parts of the graph. Unlike DFS, BFS detects cycles by checking if a newly discovered neighbor has been visited before. However, it requires careful management of predecessor information to differentiate between valid tree edges and potential cycles. Both BFS and DFS have similar asymptotic complexities but differ in space usage patterns. BFS tends to consume more memory due to its level-wise expansion strategy compared to DFS's linear recursion stack. Applications beyond academic interest. Cycle detection finds critical applications in various industries. Software engineers use it to validate hierarchical data structures, while network administrators rely on it to detect redundant links in communication infrastructures. In finance, cycle detection helps identify suspicious transaction patterns indicative of money laundering schemes. Healthcare professionals apply these principles to analyze patient referral networks for anomalies. Machine learning researchers leverage cycle detection to prune neural network architectures and optimize training processes. Game developers employ these algorithms to prevent infinite state transitions in AI behavior trees. Case study: social network analysis. Social media platforms extensively use cycle detection to manage friend recommendation systems. By analyzing connection graphs, they can identify cliques or communities characterized by dense interconnections. When detecting cycles in user interaction networks, platform engineers must balance between accurate anomaly detection and preserving legitimate relationship formations. False positives could lead to unnecessary account restrictions. Specialized algorithms modify standard cycle detection techniques to account for weighted relationships, temporal factors, and dynamic changes in network topology over time. Performance considerations: large-scale graphs present unique challenges requiring optimized implementations. Memory management becomes critical when dealing with billions of nodes and trillions of edges typical in modern big data applications. Distributed computing frameworks often implement cycle detection across clusters, partitioning graphs into manageable chunks processed concurrently. Careful synchronization ensures consistent results despite parallel execution. Approximate algorithms trade precision for speed, providing acceptable accuracy for very large graphs where exact solutions become computationally prohibitive. These approaches find application in real-time analytics scenarios. Advanced topics in cycle detection: researchers continue developing specialized algorithms for particular graph classes. Planar graphs benefit from Euler's formula-based approaches, while bipartite graphs offer simplified detection strategies due to their structural properties. Tarjan's algorithm extends basic cycle detection capabilities by identifying strongly connected components in directed graphs. This provides richer insights beyond mere existence confirmation. Probabilistic methods introduce uncertainty measures to quantify confidence levels in cycle detection outcomes. These techniques prove invaluable when working with noisy or incomplete dataset sources. Practical implementation guidelines: successful implementation requires attention to several key factors. Choosing the right data representation format, adjacency lists versus matrix representations, significantly impacts performance characteristics. Edge directionality plays a crucial role in determining which algorithms perform optimally. Directed graphs may necessitate separate treatment for forward and backward edges during traversal. Error handling mechanisms should address common failure modes, including invalid input formats, memory allocation failures, and unexpected termination conditions during long-running computations. Future directions and research trends: ongoing research focuses on improving existing algorithms' efficiency and expanding their applicability to new problem domains. Quantum computing promises novel approaches to classic graph problems with fundamentally different computational paradigms. Machine learning integration opens exciting possibilities, enabling self-improving algorithms capable of adapting to changing graph characteristics autonomously. Hybrid approaches combining traditional algorithms with learned behaviors show promising results. Cross-disciplinary collaborations between mathematicians, computer scientists, and domain experts will likely drive future advancements. Innovations in hardware architecture also promise to reshape our computational landscape for graph processing tasks. Conclusion: cycle detection remains a fundamental aspect of graph algorithms with wide-ranging implications across numerous fields. Mastering these techniques equips programmers to solve complex problems arising in diverse technological contexts. To deepen your expertise, experiment with implementing different cycle detection methods on varied graph types. Explore open-source libraries containing optimized implementations and study their source code to understand advanced optimization techniques.